Physics notes, units 6.1 to 6.3. We might not finish all of 6.3, so I'll say 6.3a. But it has to deal with circular motion. Let me come back to that, though. A little review. There are some concepts in physics that are counterintuitive. And the two biggest ones are in this first semester of physics. And the circular motion is going to be in that category. I'll explain in a minute. But when things are counterintuitive, they feel like tricks. Students, people in general, they think sometimes that physics is a trick. Well, it's because it's going against, I call it your gut. They're counterintuitive. Here's one that we've had so far. Newton's third law, which is as simple as it can be. For every action, there's an equal and opposite reaction. And we went over some of that already, but let me just remind you, we fall into traps. And once again, we might call them tricks. They're not tricks. For every action, there's an equal and opposite reaction. I use this example. A ball is falling through the air. A ball that weighs 2 pounds falling towards the earth. Why is it falling towards the earth? Well, because the earth is pulling on it with a force of gravity of 2 pounds of force, which is however many newtons. But if the earth pulls down on a ball with 2 pounds of force, then the ball pulls up on the earth with 2 pounds of force. Equal and opposite. That's what Newton's third law says. They pull equally on each other. It just doesn't always quite feel right. It feels like the earth should be pulling harder than the ball, but they pull equally on each other. Now, if I have a bigger ball, like a 16-pound bowling ball, now the earth is pulling harder because we have bigger masses. So the earth pulls down on a 16-pound bowling ball with a 16-pound force, but that 16-pound bowling ball pulls up on the earth with a 16-pound force. It's just like I said before, though, the earth is not affected by that force. There's essentially zero impact for that small of a force on the earth, but it's a big enough force to make the ball accelerate. Other examples, a car goes down a highway and a bug smashes against the window of the car. This has probably happened to you. All right. Does the windshield of the car exert a force on the bug? Yes. Let's say it's 1 Newton. It's probably less than 1 Newton, but let's say it's 1 Newton. Well, at the same time, does the bug exert a force on the car's windshield? Yes, 1 Newton. They exert the same force on each other. That force is just more devastating, completely devastating to the bug, and probably just makes a smear on the windshield of the car. Or if a car goes down a road, happens to hit a deer. Sometimes that happens. I'm from Michigan. It happens a lot in Michigan. Originally from Michigan. I've been in Illinois now for over 30 years. Anyway, a car hits a deer. Does the car exert a force on the deer? Yes. Now, it's bigger than the force it exerted on the bug. That's a separate situation. But in this situation where a car hits a deer, the force on the deer is the same as the force that the deer exerts on the car. It might be 500 newtons. Pick a number. They exert the same force but opposite direction on each other. This is counterintuitive, and we're going to fall into traps possibly. Another example, Earth and Moon. All right? Do they pull on each other because of gravity? Yes. The Earth pulls on the Moon with a force of gravity, and the Moon pulls back with a force of gravity. It's a big, big force. It's in the millions, billions of newtons of force. They pull equally, but the one that's more affected is the lighter mass. The lighter mass, the smaller mass, is the one that's more affected. So that's counterintuitive. So those questions feel like tricks, as simple as they are. That's probably the biggest counterintuitive thing all semester. But here's the second counterintuitive thing. Circular motion. In circular motion, things are accelerating. Even if you're in a steady circle, if you're on steady circle, which will be coming up in the middle of this page, uniform circular motion, steady circular motion, you are accelerating. You're not speeding up, you're not slowing down, but you are accelerating. This does not feel right. It's going to feel like a trick maybe. It's not. When you're going in a circle, a steady circle, you are accelerating, and you are accelerating towards the center of the circle. Even though you're not getting closer to the center of the circle. If you think about this, it doesn't really initially make sense. But because we've defined earlier that acceleration is a change in velocity over time, and we've defined velocity in its vector nature as something that has size and direction, all right? The first two cases for acceleration are easy. Speeding up, that's acceleration. We all can feel that. Slowing down, we can feel that. That's an object speeding up, slowing down. That's acceleration. because you're changing your velocity from you're increasing it or decreasing it. But when you change directions, if you're going north and then you turn to go west, you've changed your velocity. And by definition, if you change your velocity, you are accelerating. And you can calculate this acceleration numerically. The other issue we have with acceleration is most of our experience in life is with speedometers, like in cars. You have a good feeling for 25 miles per hour, 50 miles per hour in a car. You see the numbers on a dial or on a display on your dashboard. So you know what this is. Or on a bike, you know 10 miles per hour, 20 miles. You have a gut feeling for those. And our mind tends to bring us back to velocity when we get to the discussion of acceleration. You've probably never used an accelerometer. And the units are even weird. Meters per second squared. You could do meters per hour squared. You could do miles per second squared. But our convention has been meters per second squared. The units just are weird as well. And when we discuss this and when we look at the graphs, we get ourselves possibly confused because when we look at the acceleration graphs, when we look at the velocity graphs, our minds tend to go towards the more familiar velocity. We have a good feeling for what velocity is and how fast these velocities are. We don't really have a good gut feeling for accelerations, except for we're trying to learn this now and practice this so it'll become more natural as we go through this class that things that change their velocity are accelerating. Speed up, slow down. We did the uniform acceleration. We did a whole bunch of problems on that first unit test. Will also be on the midterm and final. But now we have something going in a uniform circle. But let's get some symbols here. I'm going to be very consistent with the book. Different books have slightly different symbols. But here's a circle over here. Center O, radius R. So delta theta here. Delta theta, it says it up here, delta theta is angle displacement in radians. You can do it in degrees, all right? But we want radians in this class, and that's a possible source of confusion, maybe. We won't deal a whole lot with radians in this section, but in chapter 10, we'll spend more time talking about radians. But we all know that a full circle is 360 degrees. If you go around a full circle, delta S for a full circle is 360 degrees. That's how many degrees in a full circle. A lot of you hopefully remember from math class, a full circle is 2 pi radians. All the way around is 2 pi radians. So those are basically two different units. Strictly speaking, radians are not units, but we treat them like units. Full circle, 2 pi radians, 360 degrees. So 2 pi radians equals 360 degrees. We won't be using that quite yet, but we'll talk about it. So you have the radius of the circle. Delta S, in this case, delta S looks like about 45 degrees, which is, I believe, pi over 4 radians, because 90 degrees is pi over 2 radians. You don't need to memorize any of that. Just reminding you if you remember that from math class. But delta S is an arc length, like from point A, this point A over here, to point B. That's the arc length. And those are being meters. So, okay, I'm going from point A to point B. So we have delta S. So delta theta, angle displacement, is equal to delta S over R. We'll be using that in some of these problems. Okay, up here I have if delta S. Okay, actually I miswrote that. That should say delta theta. No, I'm sorry, that's right. Delta S. Delta S is 2 pi R. I did write it correctly. In other words, if I go around the circle, if I walk around this circle, this circular path, this will come out in meters. That's the circumference of a circle, 2 pi r. Circumference of a circle is 2 pi r. So you've probably seen that equation before. C equals 2 pi r. The area of a circle, which we're not doing right now, is the area is pi r squared. It's a different formula. All right, so another thing we have to keep in mind, which we'll be using quite often, are these second two equations. Now, a new letter, omega, Greek letter omega. Omega is angular velocity in radians per second. You can do these in RPMs, rotations per minute. You might be more familiar with that. We used to have these things called records. You probably know what records are, record players, record turntables. And the common speeds, the old ones were like 78 RPMs. They spun at 78 rotations per minute. And then they had the smaller ones with the big hole in the middle. Those are 45 RPMs. And then the ones that were phased out before we started doing cassette tapes and finally CDs and so forth, which I'm not even using those anymore. But the final records were 33 1/3 RPMs. They call them long plays. So you could put more music and they lasted longer. Anyway, we're not going to be doing RPMs. The standard units for angular velocity, and it is a velocity. There's two basic directions, which we'll spell out more specifically in Unit 10. You have clockwise and counterclockwise. Right now, we'll just treat it mostly like a speed. We really don't care about the direction so much yet, but we will. So we have angular velocity in radians per second. So if you make a full circle every second, that's 2 pi radians per second. If you make 2 circles in a second, that'd be 4 pi radians per second. We'll practice this. Now, linear velocity, which we've been using so far all year long, is meters per second. And once again, we're going to treat these more like speeds, but they are vectors. Now, it turns out, and we'll see in the diagrams, that what we're mostly interested in is the tangential velocity of an object, a tangent to the circle, as we go in circular motion. We'll come back to that example. Now, another equation for omega. Omega is V over R, as you see in this equation right here. Or if I take this equation, this equation is the same equation. So this equation right here is the same equation as that equation, just reformatted. And that's probably, of these equations that are written down here, it's probably the one we're going to be using the most. Okay, back to Newton's first law again. An object at rest stays at rest. An object in motion stays in motion in a straight line, constant velocity, unless acted on by an unbalanced force. Once again, by definition, constant velocity means going straight with a steady speed. If you turn, by definition, acceleration is a change in velocity. If you turn, you've changed your velocity, therefore you've accelerated. When you turn, you are accelerating. You are accelerating towards the center of the circle of turn. Let's stick with the simplest kind of circle. I mean, a circle, a basic circle. So we're going to have what's called uniform circular motion. I want you to do a little thought experiment with me. You're thinking of a ball on a string. A ball on a string. All right? You're twirling a ball on a string above your head in a steady circle. Steady circle. All right? And sometimes we talk about 10 RPMs, rotations per minute. Pick any number. I'm spinning a ball at 30 RPMs, 40 RPMs, doesn't matter. Once again, the better units are radians per second, but I think it doesn't matter what the units are. You're spinning a ball on a string above your head at a steady speed. Other examples, which I'm not going to use right now, but that could apply, would be the Earth around the sun, moon around the Earth, even though those are not perfect circles, they're close enough. But go back to the ball on a string. You have a ball on a string and you're swinging it at okay? Is the speed constant? Well, I've already said by definition, yes. Actually, I should stipulate this. The speed, okay, that's both the linear speed and rotational speed or angular speed. Sometimes it's called rotational. Both linear speed and angular speed are constant. All right. If you're spinning something, in all these examples, if you're going in a steady circular motion, your linear and angular speed are constant. Your angular speed would be 25 meters per second. 25 radians per second, or 25 rotations per minute, whatever units you're using. The linear speed would be in meters per second. Will be tangent to the rotational speed. I'll show a diagram here in a minute. But what about your linear velocity if you're going in a circle? The speed is constant, 10 meters per second. But the velocity is not constant. It's not constant because of the changing direction. If you're going in a circle, steady speed. But by definition, the velocity is changing because of the changing direction. That's a tough one. We've got to work through that. Well, if the velocity is changing, okay, is the object accelerating? Yes. Okay. The velocity is not constant. Therefore, it is accelerating due to the changing velocity. And if it's accelerating, there is a net force because those go hand in hand. These always go together, according to Newton's second law. If it's accelerating, there's a net force. If there's a net force, it's accelerating. And they're always in the same direction. So the net force is in the same direction as the acceleration. There's a lot right here that we're going to go through with the examples. This is kind of almost a summary right now. So bear with me. What is the direction of linear velocity? If you're going in a circle, what's the direction of your linear velocity? Well, rotational velocity is either clockwise or counterclockwise. We'll come back to that. But linear velocity is always tangent to the circle. The acceleration is towards the center. It doesn't feel right, but it is. You can prove this mathematically and vectorially. The proofs are kind of involved, as I think I've mentioned before. So we're not going to prove those right now, but you are accelerating towards the center. That just does not feel right. You're just going to have to go with it for now. What is the direction of the net force? Well, the net force and acceleration always go together. So these always go hand in hand. If there's a net force, there's acceleration in the same direction. All right, so let's look at a diagram. So this is your ball on a string. I'm going to add to this. All right, actually, let me tweak my idea here a little bit. This is an overhead view of a record on a turntable where we used to play music. You put a needle on there and play through the speakers. So you have an overhead view. You're looking down from the ceiling on a spinning disc. Spinning disc. All right? And what I have here, the red dot is the center of the spinning record, the spinning disc, and it's spinning counterclockwise with a steady omega. 33 RPMs. That was a standard record speed, rotational speed. 33 RPMs. So if this thing is spinning at 33 RPMs, which you could convert to radians per second, I'm not sure what the conversion is, doesn't matter. Steady rotational speed, 33 RPMs. Both A and B, humor me here, these are little wads of gum, just because they stick. So I put a sticky piece of gum at point A and a sticky piece of gum at point B. Well, blue gum, that doesn't really matter. It's two objects that are stuck to the turntable. Sometimes they say they're pennies. Make believe they're pennies. Something stuck to the turntable. Well, if there's two wads of gum, two pennies at points A and B, at points A and B, all right, both objects at points A and B have the same rotational speed. They're both going 33 RPMs. Same rotational speed. All right? But they don't have the same linear speed. They don't have the same linear speed. The one further out has bigger linear speed than the one that's closer in. All right? So they have the same rotational speed, 33 RPMs. But point B, whatever's at point B, has to go through a bigger circle. Let's say it's twice as far out. The circle it makes in the same time is twice as big. It's covering more distance. That's why it has a bigger linear speed. Well, that's a little, you got to think about that. Same rotational speed for both, different linear speeds. Now, each one has a changing velocity. A has a velocity that's changing due to its changing direction, and B is changing its velocity due to its changing direction. But let me draw another diagram here. All right, this diagram here on the right is supposed to be the same record, and I just drew object B, whether it's a penny or a wad of gum sitting on the turntable. It's still spinning at the same omega, 33 RPMs, or you'd want to convert to radians per second. We'll do that eventually in Unit 10. So say it's 33 radians per second. All right. This is technically not a free body force diagram because V is a velocity, not a force. But here's the thing. If you're going in a circle, your F net is towards the center, and the acceleration is towards the center. Your velocity is tangent. It's perpendicular to the force. Here was the equation I had at the very top of the page that I circled at the top. And I just used the subscript T here for tangent. The velocity, the linear velocity in meters per second, is tangent to the rotational velocity that will be in radians per second. So let me try to show you a little video on this.
Newton's second law of motion as it relates to objects moving in a straight line. Turns out, Newton's second law also tells us about the net force on an object as it moves in a circle. When an object moves in a circle, its velocity changes direction. Since the velocity is changing, that means we have an acceleration. And we know from Newton's second law that if we have an acceleration, we have a net force.
Okay, to summarize the three most important new things from those first 2 pages, if you are in a uniform circle, you are steadily accelerating towards the center of the circle. Point number 1. Steadily accelerating, even though you're not getting closer. It's called centripetal acceleration, which I'll talk about here. The net force is towards the center of the circle. We call that centripetal force. It is a net force towards the center. You just saw that in that video. And the velocity at any given time is tangent to the point at which you are in the circular motion. The velocity is changing. So the velocity is tangential and changing. The acceleration is steady, not changing, but it's towards the center at all times. And the net force is towards the center in the same direction as the acceleration. Those are the 3 most important new things for this circular motion. So specifically, that acceleration is called centripetal with a P, not an F. Centrifugal with an F is another thing we'll talk about. You might be more familiar with that. But this is centripetal. It means towards the center. The equation is A sub C, where the C means center or centripetal, is A sub C is V squared, your tangential velocity, over R. That's the equation we'll be using most. But because over here on the far right, V equals R omega, your tangential velocity is equal to the radius times your rotational speed, you can plug this circle over here into this expression for V, and you get this alternative calculation for centripetal acceleration. If you know your rotational speed in radians per second. If it's in rotations per minute, you have to convert to radians per second. We'll do some of that. All right, so if you have a centripetal acceleration, you have a net force. The net force in this case is specifically called centripetal force. With the ball on a string, the centripetal force is the string pulling on the ball. For gravity problems, it's gravity pulling on the ball. For cars going in a circular track, it's actually friction. We'll show you that example. But centripetal force, the calculation is mv squared over r. It's just taking mass times the v squared over r, because that follows from Newton's second law way over here on the right. F sub c, or F net equals ma, because F sub c here is the F net. Once again, plugging in the relationship for velocity being, tangential velocity being r times omega, here's an alternative equation. So you'll always have access to these on the test. And you can rearrange these equations in a lot of different ways, but those are the 2 most common ways for each of those 2 equations. Now, the book has a section or 2 on what are called fictitious forces. Centrifugal force, centrifugal force, is an apparent outward force felt in a rotating reference frame. It feels real. That's why we call it centrifugal force. But we can't calculate this force. It cannot be calculated. We can only calculate the inward force because it takes an inward force to make you go in a circle. It doesn't feel like that way. So this is another one of those counterintuitive things. Very counterintuitive. Here's the example, a prime example. You're in a car, you take a hard left, whether you're driving or especially if you're in the back seat, but if you're driving, you feel like you're being pushed out of the circle to the right. Right, so hopefully your seatbelt is there, because if you take a really hard left-hand turn, you feel like you're going to right, and you are kind of sliding to the right relative to the car seat. But what's happening when you're in a car going straight and take a hard left-hand turn, what happens is your body, because of Newton's first law, wants to keep going straight. And as the car turns to the left, it makes you feel like you're being pushed to the right, when really what's happening relative to the ground is you want to go straight. That's a tough concept to get your mind around. But we'll talk more about that when we talk about centrifuge, when we want to separate liquids in a spinning apparatus, good medical application, which we'll talk about later on. But centrifugal force cannot technically be calculated. It's what we call a fictitious force. It's in what we call an accelerated reference frame. So we'll keep talking about that. We're not going to focus on this a whole lot, but we do want to talk about it and understand it to at least a general level. But for something to go in a circle, there has to be an inward force. But if you're the person that's in that situation, it really feels to you counterintuitive. It feels to you like there's an outward force, but there's an inward force. Here's another example that I like to use in class. If you're in a car at a stoplight, this is a linear case of the same thing. You're in a car at a stoplight, and you're in a good car. you're in a good car, and I don't, want to encourage any bad driving behavior. But let's say you're in a safe environment, and you're in a car that's a really good car, and you're in a place where you can, check out the capabilities of that particular car. You're in a racetrack or whatever, and it's a straight racetrack, and you can hit the gas pedal really hard, and the car feels like, well, it does. It takes off. It accelerates straight forward. It accelerates straight forward. To you, if you've ever been in that situation, and I think we all have, if you're just accelerating straight forward, it feels really real that something's pushing you back into the chair, pushing you back into that seat of that car, when there's not. Because if you want to accelerate forward in a car, in a good car, you have to have a forward force, because the net force, the forward force, has to be in the same direction as the acceleration. So if you're accelerating forward, there has to be a forward force on you. This is another example of fictitious forces. That doesn't have a name, so we don't have as much trouble with it, but this circular centrifugal force is a similar thing. So let me say it one more time. When you're accelerating forward in a car, think about it. You feel like you're being pushed back into the car seat. You feel like you're being pushed back into the seat. Something's pushing you into the seat. Well, really what it is, it's the seat pushing forward on you. Your body was at rest and wants to stay at rest, so it gives you the illusion in your mind that there's a force pushing back on you. That's another fictitious force, because the car is accelerating. So these fictitious forces come into play when you have an accelerating reference frame. All right? So when you take a turn, your body wants to go in a straight line, so it feels like there's an outward force when there's not an outward force, even though it feels real to you. That's a tough sell. So think about that. We won't need to worry about it a whole lot, because it's going to be pretty straightforward to plug numbers into these equations. So let's do some examples with centripetal acceleration and centrifugal, centripetal force with a P, not centrifugal, because you cannot calculate those. There's no numerical calculation or equation for that. So let's mathematically apply centripetal acceleration, centripetal force. So here's the idea where somebody's got a ball above their head and they're twirling it in a circle, and it's going in a steady circle. So the omega, which we don't really know what it is, does it say? They tell us the tangential speed, but we don't need to know the rotational speed for this particular problem. But it shows you here, like if the ball is right here, right now, this is in this spot, hopefully you can see that where I'm at right there, right? At that point, if the ball's going counterclockwise, the velocity, it's labeled here, is tangential like that. It's already labeled on the diagram, all right? And then the centripetal force, F equals ma, that's the generic statement of Newton's second law, that's F net, that's F sub c, that's the centripetal force. So the ball's going around, it's tangential anytime. So when the ball gets down here, or this spot right here, its velocity would be this way. It's tangential velocity. Sometimes I put sub t on there for tangential. When the ball gets, say, here, right, its velocity is tangential, v sub tangential. It's the same magnitude, it's the same speed at any point, but it's a different direction. That's why it's a changing velocity. And then it shows you if the string breaks when the ball is right here, it goes off in the tangential direction towards the left here in this particular overhead view. So the ball, it goes off in this direction because its v tangential was in that direction when the string broke. Okay, but let's calculate the centripetal acceleration. This is pretty much a straightforward plug-in problem, part A. We're just going to plug into a sub c equals v squared over r. We just have to check. We have to check our units. So a sub c here, it says the speed, the tangential speed is implied here, is 3.3. So it's just 3.3 meters per second. That's good. We want it in meters per second divided by the radius. Double check to make sure it's the radius, not the diameter. So that's 0.75 meters. So a sub c here, that's pretty straightforward. All right, so I went ahead a little bit here, but if you calculate 3.3 squared divided by 0.75, the centripetal acceleration is 15 meters per second squared. Coming up later, we'll say that it's more than gravity's acceleration is 10. So sometimes we look at multipliers. That's 1.5 times the typical gravity acceleration. This is not a gravity problem. So we would say that's 1.5 Gs, where G stands for 9.8 or 10, rounded off. We'll talk more about that in a little bit. But then the centripetal force is mv squared over r. So you could just take the mass, 1.5 kilograms. You want kilograms, not grams. So we have to remember to make that 1,500 grams into kilograms, and then v squared over r, or just take the 1.5 times the 15, and you might get 23 newtons, depending on how you round off here. That's F sub c, but that is the tension in the rope. That is T, which is what it asked for, is 22 newtons. Because the tension in the rope is the centripetal, it's the agent of the centripetal force here. So that you could, if you just put F sub c equals 22 newtons, I would give it to you. So once again, the string can be the centripetal force agent, gravity can be the agent, friction can be the centripetal force agent, and we'll do examples of that. Then part C says, calculate the centrifugal force. And if anything is a trick question, this is kind of in that category, so be careful. This is a conceptual question. Can't calculate. Try to stress that. Can't calculate it. All right? You can't calculate that force. It's a fictitious force. So just say you can't calculate that. All right, so that's example number 1. All right, so probably the hardest part about this problem is the conversions, but let me just summarize. You have over here on the left, the moon and the earth pulling on each other with the force of gravity. They pull equally hard on each other. The smaller mass is more affected. The moon is more affected by that force. The moon has a centripetal acceleration, v squared over r. In the problem, it tells us the radius, make sure it's in meters, which it is. I'll plug that in a minute. But I have to figure out the velocity of the moon. Well, the basic equation for velocity is v equals delta x over delta t, how far you go in a given amount of time. Now, it tells me, and this is kind of a fun fact, that you really kind of should know this, it takes like 28 days for the moon to go around the earth. That's how long it takes the moon to go around the earth. So we get a full moon every 27 days. We get a new moon where it looks, dark every 27 days as well. 14 days later-ish. 14 plus 14 is 28 if you round off a little bit. This is where the months originally came from. Most of you probably know that, but just a little history there. But you should know that. It takes the moon about 27 days to get around the earth. Anyway, so the basic equation, though, for velocity or speed is how far you go. Well, when you're going in a circular motion, your delta x is 2 pi r. That's the circumference of a circle, 2 pi r. So that's how far the moon goes in the time of 27.3 days. But we want seconds. On a test, you don't need to show me that conversion. Just do the conversion on the homework. It comes out to be 2,360,000 seconds every month. Wow, that's a lot of seconds. In scientific notation, that's 2.36 times 10 to the 6th. So calculate the velocity of the moon. The tangential velocity of the moon, it's 2 pi r, the radius, divided by the time, not squared. And it comes out to be like 1,020 meters per second. That's like 2,000 miles per hour. That's the speed of the moon. It's got a long ways to go every month. It's got a pretty high speed, in the 2,000-ish, give or take a little bit, miles per hour. Now I'm going to calculate the centripetal acceleration of the moon. A sub c is then 1,020, and I can have 3 sig figs there because all the numbers that was given was 3 sig figs, divided by the radius, v squared over r, which is once again 3.84 times 10 to the 8th. It's times 10 to the 8th. So the centripetal acceleration of the moon. So once again, I plugged the numbers in and worked ahead a little bit. The centripetal acceleration then is, and don't forget to square this, 1,020 squared divided by the radius, which was in meters, gives you a centripetal acceleration of 2.7 times 10 to the negative third meters per second squared. It's a very small acceleration. And then you can replug all the numbers in or just take your answer from part A and multiply by the mass of the moon, which was given to be 7.35 times 10 to the 22nd kilograms. Double check the kilograms. Plug it all in again, or just, like I say, multiply mass times the acceleration, and you get a very large force. The centripetal force on the moon is 2 times 10 to the 20th newtons. That's how hard they pull on each other. But it's enough to make the moon go into this circular satellite orbit, and the Earth just kind of wobbles a little bit. It's not completely stationary. It wobbles because of this force. All right, let's practice. Well, let's probably tie this video up and then start another video. But let me also say this once again. When you're in circular motion, steady circular motion, there's steady, constant acceleration towards the center, centripetal acceleration. Constant steady force towards the center, centripetal force. And tangential velocity that's changing due to its changing direction at all times. It's a steady speed. Linear and rotational speeds are steady, but the velocity changes due to the change in direction.